Greetings and welcome to Module 7, Statistics and Education. I am broadcasting to you nearly live from my home office on October 19th. This week we are going to be discussing, as you can see in the PowerPoint slide, we're going to be discussing statistics, and we're going to be focusing on descriptive statistics and inferential statistics. To prepare for our discussion, your reading assignment is Chapter 6 and Chapter 7 in our textbook. One thing I want to say to you is that I realize statistics comes with a bit of stress and sometimes some math phobia. So I wanted to set your mind at ease that we won't be doing any calculations in this class, that we're just going to talk about concepts in general and then be discussing them in our classroom forum. So join me in discussing statistics now, won't you? Our first concept is this idea of descriptive statistics. And descriptive statistics are merely a way of describing a sample. So we might apply the concept of the bell-shaped curve to see how distributed a sample may be. So we want to see if it's normally distributed, which is preferential, or if it's skewed to the high end, meaning that the lump of students or whoever we're measuring is clustered at the high end, or likewise it could be skewed to the left at the low end. So any of those two types of distributions sort of looking like a lump in either one end or the other end of the standard bell-shaped curve is problematic. So we use descriptive statistics to make sure that the sample we're going to be talking about, or the two samples we're going to be talking about, are appropriate for our uses. So the first concept we're going to talk about, and really the only concept in terms of statistical analysis with regard to Chapter 6, is this concept of correlation. And concept of correlation is fairly easy to get once it's explained. And that is, we are measuring the relationship, possibly using a Pearson product moment, for instance, looking at the R, of between two things, such as, let's say, a grade point average and success in graduating from school, from, let's say, high school here in Chicago. So what we're looking at is we have a scale from -1 with 0 in the middle to a +1. And when the mathematical computation shows that there is a positive relationship, it can be anywhere on that scale from just above 0 to +1. +1 being absolutely positive, 100% positive there is a relationship, which obviously is difficult to get, to very close to 0, which is minimally related. And what this does is this allows us to discuss the relationship between the two, not necessarily causality, but to assign a level of trust or a level of certainty that these two things are related. So we might be able to make a policy decision that those who have high GPAs are going to graduate and go to college. And so we might be able to look at those with low GPAs, flag them for interventions. And this is the kind of usefulness of a correlation. So let's look at that. So on the positive side, we might look at a 0.3 relationship, a 0.5 relationship, and a 0.75 relationship. The 0.75 relationship is highly correlated. The 0.5 relationship is moderately correlated, and the 0.1 or 0.2 relationship is minimally correlated. So our strength in confidence of the two factors being related on a 0.1 is minimal. A 0.75 would be they're highly related. Doesn't mean there's causality, but it means they're highly related. And we might be able to, from that 0.75, generalize using a correlation that those with high GPAs are highly likely to graduate. And that way, we might say that this group is doing well. And likewise, if we see a very low correlation, we might say that the relationship between high GPA and graduation are mildly related, and then that means we couldn't use with certainty that those with low test scores are not going to graduate. There's independent variables that could be related, intervening variables that could be related to those with high test scores, like getting a job or anything along those lines that could change, they could take away time or change that graduation. So that's the idea behind correlation. Now, let's talk about inferential statistics. And inferential statistics are basically this concept that we can make an inference, not causality, but a very strong inference that the dependent variable was responsible for the effect, and that then we can generalize from that sample, from that effect of the dependent variable, that we can generalize to the entire population, that would be good for the entire population. And let's use an example. We're comparing the means using a t-test between two groups. Let's say we're looking at Singapore math. One group gets Singapore math as a treatment. The other group does not. It gets normal standardized curriculum, let's say something similar to everyday math formerly used in CPS schools. And then the ultimate test is going to be PARCC testing, and the math portion of the PARCC testing. Now, what we can do with the t-test is we're going, as you can see on the sample slide, we're going to compare means. T-test will compare means, and from the comparison of the means, we can infer if the treatment worked or not, and if we should generalize the treatment to the whole population, let's say CPS. So we compare the two means, that we implement the t-test, we apply the t-test, we compare the two means, and we find that Singapore math is significantly higher than the standard curriculum that the other CPS, the other sample group, received. Assuming that both samples are nearly normal and nearly comparable, then we know there's no variables, intervening variables or moderating variables, that may account for the difference in the mean test scores or difference in the t-test. So what then we can see is that if the Singapore group tests significantly higher than on the PARCC testing, then what we can generalize, what we can say, is that with a high amount of confidence that we can infer it would be Singapore math would be beneficial for the entire school population. Then we can make a policy decision based on this t-test, and we could confirm our hypothesis that in fact Singapore math is going to be good, is going to produce better test results than the other standardized curriculum. And if that was our hypothesis, then we can use the t-test to hypothesize this, because that's what we're testing, is assuming that that is our hypothesis, that Singapore math is going to be beneficial. So that is how we then come up with our conclusion, we validate our hypothesis, then we generalize it, we make a policy decision and generalize Singapore math to the entire Chicago public school system. So in essence, very short, that covers our my video lecture for today on for this week. Again, we are covering the basics here, so there are no computations. The discussion question is basically going to be discussing a t-test, the results of a t-test, and if those results, if one result is better than the other, and to discuss why. So thank you for tuning in, and I look forward to seeing you in the class discussion.